Here we're going to talk about one of the basic components of calculus. In fact, there's two basic components, the derivative and the integral. And here we're going to talk about the derivative, just the basics. I'll make another video going over maybe a simple example of how to take a derivative numerically, as well as maybe a more complicated one of my favorite functions, the application to physics, the position vector, looking at velocity and acceleration. Uh, One of the first things to remember, and the biggest thing to remember about derivatives, is this term right here, as I put slope everywhere. That basically sums it up. You can't say it any better, and you'll understand that a little more as we move along. Let's get some definitions out of the way. According to a book, it would be the rate of change in some dependent variable, in this case y, with respect to the independent variable x. You'll remember from algebra that I say f of x or y equals, those are equivalent statements, equals something. The f of x is the dependent variable, which is dependent upon the value of whatever comes after f of x. The That's pretty wordy definition there. Basically, what it's saying is uh, it's a slope. We're looking at the same thing as we do in algebra when we talk about the change in y over the change in x. How from point to point, how does this function move up or down and left to right? Uh, it's a ratio of its movement in the north-south direction over the directions east to west, how far it moves. That's the definition of slope, and we'll look at that numerically in just a minute. Kind of rambling here, but the notation that's commonly used is dy over dx. This is read as the derivative of y with respect to x, or I prefer the notation f prime of x, especially because I just kind of like it. It's nice and clean. I usually use f of x for my function, so this kind of just is the next logical step. Um, so to understand this whole idea of slope everywhere and this complicated definition that I rambled about, let's take a look at exactly what is slope. Not just in calculus, but let's go all the way back and talk about slope in terms of algebra. So the equation of a line, y equals mx plus b, remember all the way back to high school. And let's just give this some values such as y equals x. That's a simple one. So let's draw our coordinates, our Cartesian plane, mark off some units. Doesn't really matter in this case, you'll see. And that's y equals x. When x is 1, y is 1. When x is 2, y is 2. When x is 3, that's 3, so on and so forth. Negative, same thing. So this is our line, and our slope obviously is rise 1, run 1. Rise over run, or delta y over delta x equal to, we change 1 unit, 1 over 1. The slope equals 1. Remember, slope is m in that formula. So here we have y is equal to x, as we said, and the slope would be that 1 that is understood to be there. B, remember, is the y-intercept, and of course it crosses the origin, which would just be 0, leaving you with this. So I guess we've proven that this is the equation of that function about plotting points. The point that I was getting at is that when you have a line, of course the slope, no matter where you took it, would be the same, no matter where you are on this line. But what if we had something that was y equals x squared? Let's change this to f of x is equal to x squared, which is equivalent, correct? Well, what we have there, of course, if you're looking at calculus videos, you should probably be able to recognize this without a table of values. It's a simple parabola. Of arbitrary values, x, y. I forgot to label my axes. Alright. Point being here is that if the slope is the same 1 over everywhere on a line, algebra is sufficient to find the slope of a line. Like I said, it's just y2 minus y1 over x2 minus x1, or delta y over delta x. This being, let's call this y, or sorry, x1, x2, I cannot do this, y1, x2, y2. This would give you a slope, plug these values in, get this, and it's going to be the same for every arbitrary choice of those values. Either way, in calculus, obviously, the benefit is that we can not only get the slope of lines, we can get the slopes of curves, things where the slope is changing with every value of x as you move along the axis. So if we looked at the slope here, I'm going to try to mark it in red. Just say that's the slope there, that's the slope there, that's the slope there. It's a tangent line is what we call that. The derivative and the slope of the tangent line are equivalent. That's another term for it, essentially. A lot of problems will ask you to find when the tangent line is 0 to a function, which would be something like this. This gives you local maximum or minimum values. So every time you have this little swoop here, means you've reached some maximum or minimum value. That means your slope has gone to 0 if you can solve algebraically for these points. Helps you in evaluating functions. And I'll try to stop knocking the camera around. The point I was getting to is we need to use calculus to get these slopes. It turns out that the slope here, here, and here all could be represented by the same equation dependent upon the variable x that corresponds to the point it touches. A tangent line, by definition, say we have some curve like this, only touches at a single point and then continues on from there. That point, what we can do is plug in that x value and find the slope at that point. And the reason we call it slope everywhere, as we said, is the derivative gives you an equation you can plug in for any x value, which will give you a slope at that point on the function, specifically on curves. Like I said, with algebra, you cannot figure this out no matter how much of a genius you are. So I think I have about 2 minutes, and I'll take a look at numerically how to do this. If we have the function f of x is equal to x squared, taking the derivative is, well, let's just do it here. This is the general formula I'm writing here. The derivative of this, so you would write the dy of dx of f of x. The derivative, we're taking the derivative of f of x, which is x to the n, equals f prime of x. I'm going to tell you this is the notation I preferred. And this would be you bring your exponent down as the coefficient, so it would be n times x, and then subtract 1 from your exponent, n minus 1. So quickly, let's do this right here. We have f of x is equal to x squared, so let's take the derivative. F prime of x would be, move this down, make your coefficient your variable x, subtract 1 from 2 is just 1, which is understood, and your f prime of x for x squared is 2x. So there we've looked at what the derivative is, a simple definition, a really simple example, and why it's important as far as calculus versus algebra. This is pretty quick and pretty sloppy, so I'm sure I'm going to want to go over few other complicated examples. So I'll post that in the next video.